Hello, this is part two of Gödel and time travel, where I took some hints from Math for Physics. Math for Physics is his online name. He does videos on very rigorous videos on mathematics and physics, and he took issue with the idea of time travel. He does not really believe that it's possible, and I think that his arguments go more along the lines of the grandfather paradox, and I would guess also quantum mechanics would the whole uncertainty principle would seem to mitigate against time travel unless one takes the many worlds interpretation of quantum uncertainty. However, he has been very helpful, and I would say that what I'm going to do is I'm going to incorporate some of his some of his constructive suggestions, and B, I'm going to incorporate reference that he gave. Okay, here goes. Let's see. He wanted me to give the equations for, he wanted me to incorporate general relativity and not just special relativity. So what I did is I just downloaded a little bit on general relativity. Here we have time dilation as affected by gravitation. So the time dilation is equal to 1 minus gh over c squared, where again, TD is the total time dilation at a distance position between two objects. G is the acceleration of the box as measured by the base observer. Now you got to think of like an elevator crashing down, sort of accelerating. You got to think of it as free fall acceleration. Okay, that's G, as in like G due to gravity. If you had a box falling. And then h would be the vertical distance between the observers. So what you're looking at is not really an ordinary box falling due to gravity. You're looking more like you are standing on the event horizon of a black hole, which is impossible, but let's just do it as a thought experiment. You're looking at an object falling towards you. Okay, that would be this. That's not very good there. Okay, there we go. TD is equal to 1 minus GH over C squared. Now, the more relevant formula to what we're dealing with here is TD is equal to the square root of, we're looking at a rotating disk, okay, and we're trying to analyze the possibility of time travel. TD is equal to the square root of 1 minus r squared omega squared over c squared. Now, r omega would be the velocity of the rotating object. In other words, r would be the radius, and omega would be the change of angle with respect to time. So what you now have is basically something very, very similar to square root of 1 minus v squared over c squared, which would be the formula for time dilation that you're more familiar with, which would just be, acceleration to speeds near the speed of light. But here you have basically the same formula, but it's reinterpreted according to Kurt Gödel. So I would actually say, to be honest with you, as much as, with all due respect to Math for Physics, as much as you could discuss general relativity in this context, especially since, in fact, in my last video, I did go into the equivalence of acceleration to gravity. I would say that this actually would be the formula we would go with, and it would correspond more to special relativity. Now, that's my opinion, but that's not necessarily Gödel's, the way he derived it. And so I would say, between myself and either Math for Physics or between myself and Gödel, you probably would better off go with either of those two. So I'm going to go ahead and follow along the lines of Math for Physics and his suggestion of properties of the Gödel metric by Mario Palescano. And here's the website for it, www.math.toronto.edu/walid/mpalesciano.pdf. You can freeze that if you want and copy it down, where he goes more into Gödel's actual formulae, and they're very advanced. They get into a lot of integration and a lot of, I can follow them, but they're very advanced. But my intuition tells me that Gödel, what he probably did, okay, if my intuition tells me is he probably worked with this formula here and expanded it out, which really isn't that much different than what I was using last time. Now, it doesn't address a lot of the paradoxes involved with backwards in time travel, like what if you go back in time and change something. It doesn't address the quantum physics argument of, again, if you have quantum, the argument would be you have an uncertainty in the position of a particle before you detect it. So once you detect it, it can be anywhere within the de Broglie wave that it could potentially be, which is a probability wave. Therefore, in the quantum worldview, you really don't have a certain arrow of past to future. The future has contingency built into it. Now, there are those who have other interpretations. There are those who believe you can preserve determinism in quantum mechanics. There are those who favor a mini-universes perspective. But for those who genuinely take the, let's say, the Copenhagen interpretation of quantum mechanics, you would probably be fast to figure time travel into that. So again, it's very speculative. One book I'm looking at right now would be The Time Traveler, and I haven't gotten very far into it, but his name is Ronald Mallett. Oh, you can't really see that. Okay, so just show you the cover. The Time Traveler, one man's mission to make time travel a reality. And Dr. Mallett is one of the first I think one of the pioneering African-American physicists, at least in the United States, one of the first black physicists to get his PhD, or at least one of the first before a major wave of integration and a genuine focus on equality in education. So, he had to overcome tremendous hardships, and the death of his father prompted him to imagine himself going back in time and seeing his dad again one more time. And that eventually led to science fiction, and it led to a lifetime of exploring the question of time travel, eventually his physics PhD. So once again, it's Ronald Mallett, the Time Traveler. And I haven't finished it all the way through, but it does go a little bit into Kurt Gödel, but it also goes, I would presume, a little bit further into addressing some of the quantum mechanical questions and some of the other, some of the paradoxes. All right, well, this concludes Gödel and time travel. Thank you very much. I appreciate it.